Okay, I brought the Scantrons for the test. I brought them over to processing this morning. So usually if I can get them in there in the morning, they have them done by the afternoon. And then I'll try to grade your free response this weekend. And I'll post results, and hopefully we can talk about it Monday. Okay? Did it reflect what we've done so far, the exam? You good? Okay, good. We'll see how the results are. We'll see how good of a job I did. I guess that's what I'm trying to say. All right, so today we're going to talk about linear functions. So we talked a lot about constant rate of change, which is like the twin of linear function, and linear function is going to be what we do today is going to be really important for when we start getting to the calculus, which is next week we're going to start knocking on the door of actually starting calculus. We just got a few more pieces to put in place. Everything we've done so far is about quantitative reasoning. Okay, what is that? That's how quantities vary, especially together. And this is kind of the foundation of all calculus. This is where calculus lives, in this idea of how quantities vary together. So that's where we're practicing all this stuff. We're representing it visually. We're representing it symbolically, right, with function notation. So we got to get all the nuts and bolts in place before we can jump at the calculus. So let's talk about linear function here. So here's a scenario. Two painters. They've started painting their respective houses. At a certain point, the first painter has already, we'll call him P1, he's already painted 100 square feet. Second painter has already painted 400 square feet. Okay, so how could we represent this visually? So the information given here, how could we represent it visually? You have yes, sir?
One bar that's 4 times as long as another bar.
One bar that's 4 times as long as another bar. Is this what you were thinking?
Yeah.
Okay, so top bar represents which painter? John? Look at that. Green bar. Which painter does that represent? P2. Second painter. First painter, purple bar. Okay? So we want to define some variables x and y here. Let's let x be the area painted by painter 1. In square feet. And y will be the area painted by I think my handwriting is digressing here. I thought it would get better on this thing. Okay, can you read it? Area painted by P1 in square feet, area painted by P2 in square feet. So we're showing which x or y down here. X is the purple, y is the green. Okay? Okay, so now I'm going to say that painter 1 is going to paint an additional 100 square feet. Okay? So I'm going to represent that. How would that be represented with a purple bar, an additional 100 square feet? What would you see? Sam?
The purple bar would now be 1/2 of the green bar if you add 100 to it.
Just the purple bar. If I'm gonna.
The purple bar doubles.
Yeah, exactly. So I'm gonna. This thing is a little hard to control, so give me a second. Got it. That was fast. So what did I do? Painter 1 just painted an additional 100 square feet. And here's showing what happened to painters 2. Painter 2's additional area. So the question is the total amount painted by painter 2 proportional to the total amount painted by painter 1? Savannah is, why not?
Because or else it would have been double. The green would have gone 4 spaces instead of 4.
So if painter 1 paints twice the amount, then painter 2 ought to paint twice the amount. And did he? No. Okay, so the total amount painted by painter 2 is not proportional to painter 1. Agree with that? Okay, so why might I have shown this additional amount here as a thinner line? Why might I have shown that as a thinner line? What might that represent? Charles, any idea? Charles, right?
Yeah.
So why would I have shown that as a thinner line, maybe?
Shows the change.
Okay, and so how can we write that? What's the symbol for that?
Delta X.
Delta x, right? Nice. Richard, is that what you're going to say?
Yep.
Okay, similarly, we got the corresponding change in y. Okay, what was the initial amount of how much painter 1 had painted? 100. So that black line right there is 100. So what's the new amount that painter 1 has painted, the new total amount? Where did the 200 come from? Where did the 200 come from in terms of what we got up there? Jeff, this Jeff right here. Okay, yes, so 100 plus the change, right? So the old amount plus the change gives you the new amount. And that new amount is 200. Okay, what was the initial amount corresponding to 100 for painter number 2? That was given, he had painted 400. And so how would you find out how much he's now painted? What would the process be to get his total amount painted now? 400 plus delta y, right? And what does that appear to be now?
550.
Looks like 550. Can you see the green in the back? Well enough? So the total amount painted by painter 2 is not proportional to the total amount painted by painter 1. Is that right? Okay, so here's another question. Does the amount painted by painter 2 vary at a constant rate with the amount painted by painter 1? Now, first of all, is that a different question or the same question? Does the amount painted by painter 2 vary at a constant rate of change with the amount painted by painter 1? Different question? Tell me your name and the picture.
Chrissy.
Chrissy, do you say yes? It's a different question.
Yeah.
Okay, and what about answering that question? Does the amount painted by painter 2 vary at a constant rate of change with 1? Don't know, or not sure? Connor.
Well, you can't tell just by that one. You have to see if he would do it again.
Why? What?
Because you don't know. Maybe he just worked really hard that time. He's going to paint slower next time.
Okay. Because what does constant rate of change mean? So mathematically, how do we know that two quantities are in constant rate of change? We've been working on it for 2.5 days. Will?
Don't they have to be proportional and change simultaneously?
What's they? So be specific. You said what they have to be proportional. What's they?
X and Y, the two quantities.
So the two quantities x and y have to be proportional for constant rate of change. Is that right? This will. What's that? The change in x and the change in y have to be proportional. Which is it? We already said that y is what? Not proportional to x. The total amount by painter 2 is not proportional to the total amount by painter 1. We doubled painter 1, though painter 2 did not double. So, one more time. What does it mean for two quantities to vary with constant rate of change? Richard.
The quantity of delta y over the quantity of delta x should be your k-value
Okay.
relationship.
Right.
Or create your quotient, so you have the linear relationship after that point.
Okay. And like Will said, it's the changes in y and x that have to be proportional. Can we tell if the changes in y and x are proportional at this point? No. So this is what we're going to do. You're going to take a couple minutes. You're going to make two tables. A table of x and y, and a table of delta x and delta y. So just from all the information I've given you so far, how many ordered pairs x and y do you have, and how many ordered pairs delta x and delta y do you have? So when you get a partner, even move your desk a little bit so you're actually working with that person. So how many ordered pairs of x and y do you have so far? How many ordered pairs of delta x and delta y do you have so far? And figure out what they all are. Go.
Altogether, you counted 0 at point? Just put it anyway, so points. Yeah, because that ending point is still
Okay, Patrick, give me one ordered pair of x and y that you know.
100, 400?
Okay, Patrick wants 100, 400 for one of the ordered pairs. Agree?
Yeah.
Is there another one that we have? Andrew.
550.
What is it?
200.
200, 550. Okay, how about an ordered pair of delta x and delta y? Somebody new. Bailey, did you get it? 100 and 150. Agree with that? Any other that we know? Is there any other delta x that we know with a delta y? No. If you thought no, you were right. Okay. Keep going.
Yeah, so it's like 300 for X.
so 500,000.
Yeah.
Yeah. X and Y.
400 for flat.
Well, do we know that? Yeah. So he's asking, when painter 1 has painted 0 square feet, did painter 2 paint 0 square feet? Yes? No? Or other? We don't know. Yeah, we don't know. All I told you was at a certain point in time, this one had painted 100, painter 2 had painted 400, and then I showed you increasing delta x from there. Okay, can someone give me a delta x and delta y now? So, is it Jimin? Tell me. And how'd you get that? So 500 and what?
Oh wait, no, that's for X and Y.
Oh, that's for x and y. Okay, great. So 500 and 1,000? Agree with that? So is this 10 of those bars and this is 5? Great. Okay, how about a delta x and a delta y? 300. How'd you get that?
I found the difference from point 2 to point 3.
So did you look from here to here for delta x, the new delta x? Is that what you did? Okay, so that's good. So that's totally valid. So now starting at 200, she took this one, delta x2, to be 300, and then looked at the corresponding delta y2. Did anybody do something different for delta x, delta y? Tell me your name. Danny. Nice. And what was that? 100 to 500 is 400, corresponding delta y. Nice. Did you see how just by changing it one time, you can get 2 more delta x's and delta y's out of that? You could get, Jim had said the new delta x corresponding to the new delta y. And then Danny said, going back to the original, the full delta x from 100 to 500 corresponding to the full delta x 400 to 1,000. Okay, so I ask you again, is the total amount of area painted by painter 2, is that a question?
Oh no, I have an answer.
Oh, an answer to what?
You said that again, so I was just assuming is it going in constant?
Okay, yeah, so same question again. Is painter 2's area varying at a constant rate of change with painter 1's area? Well,
Yes, it is.
Because?
It seems as though delta y is equal to 3 halves delta x.
okay, and we said that that was constant rate of change. Was that changes in y always equal what? We better know this by now. You were rolling your eyes at the end of last class. We get it, we get it, we get it. So we better know that. Delta y equals k delta x. So, is it true? Is the additional amount that painter 2 paints, delta y, always a constant multiple, k, of the additional amount that painter 1 paints? And you said that that constant multiple is? 3 halves. So our k value, delta y over delta x, 3 halves or 1.5. So let's just rapid fire here. Can we get 3, 4, maybe 5 different interpretations of that number 1.5 in this scenario? The meaning of that number 1.5. Anybody?
I was scratching.
You were scratching your head.
I can answer.
Good time. Yeah, tell me one interpretation of the 1.5.
For every 100 square feet that painter 1 paints, painter 2 will paint 1.5 more.
Okay? Does it have to be 100?
Or for every 1 unit, 1 square foot,
Okay, so for every 1 square foot that painter 1 paints,
will paint painter 2 will paint 1.5 more.
painter, and how much is that? Yeah, square feet. Yeah. Painter 2 will paint 1.5 square feet. So if painter, for every 1 square foot that painter 1 paints, painter 2 will paint 1.5 square feet. Another interpretation of 1.5 from what we talked about. Somebody else. You, Tom?
Yes.
You, Tom.
So painter 2 would paint 1.5 times faster than painter 1.
Painter 2 paints 1.5 times faster than painter 1. Agree with it? Good, excellent. What else? 1.5, what does it mean? Practicing from last time. What is constant rate of change? Saskia.
Rate of painter 2 in terms of painter 1.
Okay. All right, so the amount painted by painter 2 relative to the amount painted by painter 1. Relative size. The amount of area painted relative to the amount of area painted by painter 1. Good. Anything else that 1.5 means?
Could you take the inverse of that and say that painter 2 paints 2/3 as fast as painter 1?
Try it again. Yeah, you could. But
I'm trying to.
who paints 2/3 as fast as who?
Painter 1 paints 2/3 as fast.
Sure. Yeah, that's right. Yeah, because it'd be delta x over delta y would be 2/3, meaning that painter 1 paints 2/3 as fast as painter 1. Anything else that 1.5 means? Any additional amount painted by painter 2 is always 1.5 times whatever amount painter 1, additional amount painter 1 paints. Is the total amount painted by painter 2 1.5 times the total amount painted by... You're shaking your head. Tell me your name again.
Kristen?
Kristen.
No, it's not.
Why not?
Because if
Which table would you look at to answer that question?
X and Y.
X and Y. So by saying that, we're saying, is the total amount always 1.5 times the total amount of painter 1? No. So this is times 4, this is times something else, this is times 2, right? So the total amount is not proportional, but changes are. What's the formula for slope? Remember, you did this. You memorized it. You plugged in numbers. What numbers did you plug in the past? y2 minus y1 over x2 minus x1. And we had so much fun doing those, right? It felt so good. Oh, I know what y2 is. I'm going to put it there. I know what y1 is. I'm going to put it there. I'm going to get my calculator out and punch. Okay, but we know better now. So what does that represent? y2 minus y1. Change in y. And x2 minus x. So would you look at that? What is slope? What is slope?
K.
It's k. It's this what? It's this rate of change, or this multiplier, this constant multiple that gets us from changes in x, always multiplied by that to give us change in y. What do I need to do to my visualization so we can relevantly talk about slope? So slope is a visual thing, right? It's the number. True, it's the number 1.5, but then it has a visual meaning. What do I need to do to my picture so that we can start talking about slope? Saskia?
Oh, I was just thinking.
Oh, I'm sorry.
Maybe like turn it.
Turn it. What's it?
The graph, the lines.
Turn both lines?
No, turn the top line vertical.
She wants to turn the top line vertical. Turn the top line vertical or the bottom line? Patrick, why the top?
Because it's, if you're in like Cartesian coordinate
Right.
system, that's the y.
Yeah, so x, we want x to stay horizontal, and then y we want to be vertical. Where am I going to put it? Where am I going to put that bar? What if I turn it vertical? I'm going to erase all this stuff. Is that okay?
Yeah.
Let's go back and start again here. Zoom out. Okay, so if I want to talk about slope, it's a little too dark. Hold on a sec. How about that? Can you see those? Is that better? Yeah, okay. So if we want to talk about slope, so now what's going to happen is I start increasing x and keep this bar on the edge of it and let y increase also. Can you imagine what's going to happen? And I'm going to put the plane. This red dot is like the plane, remember the plane leaving the trail? So anywhere the plane goes, it's going to leave a trail. So we're going to increase x, we're going to increase y, and then the plane's going to leave a trail as we go of everywhere it's been. Okay, so talk to the person next to you. Where do you see delta x in this picture? Where do you see delta y? Where do you see x? Where do you see y? So those four quantities, how are those represented in this picture? X and y, delta x and delta y. Tell your partner. Go. So I gave you some help there. So how is delta x represented in this picture? Is it Dalton? Yeah. Tell me how is delta x represented in this picture? Bottom half, like all this in here? So which color? Nice. That's our delta x, right? How is delta y represented? Crystal? The red line. Okay? And we know that, what is delta y over delta x? Oh, actually, so and what is this now? What is delta y? In delta y and delta x in this case? 1, 2, 3, 4, 5. Says it's 6? What's delta y? 1, 2, 3. How much? 900. Delta y over delta x, confirming it, is 900 over 600, 1.5. Okay, what if I go delta x of 100? What will delta y be? 150. What about delta x of 200? How does the line show constant rate of change? Can anyone articulate how is a straight line showing constant rate of change? Ben?
It goes up 1.5 units for every 1 unit that goes horizontally.
Okay, that's a nice way to say it. It goes up 1.5 for every 1 unit it goes horizontally. So therefore, if it goes 100 units horizontally, it's going to go up how much of that? 1.5 of 100. And if it goes up 200, if it goes horizontally 200, it's going to go 200 times 1.5 up. So as long as it's always 1.5, you're going to get a straight line. And that the inclination of that line, the steepness of the line, is showing this, how much faster painter 2 is painting than painter 1. 1.5 times as fast. No matter what delta x I take, my delta y will be 1.5 times that. And that, as long as that stays constant, you'll get a constant slope. And that slope is 1.5. Okay, so we said that the changes or the additional amount that painter 2 paints is proportional to the additional amount that painter 1 paints. They're varying at a constant rate. So how is it, just going back to the beginning, if that's true, how is it possible that when painter 1 had painted 100, painter 2 had painted 400? I thought we said that painter 2 always paints an additional amount, 1.5 times whatever additional amount painter 1 paints. So how could it be possible that painter 2 would paint 400 at the time that painter 1 had painted 100, which is a relative size of 4? Calvin, was it? Yeah.
It's just a starting point,
So say more about that.
Basically, you can say it's a function of like y, where you can say like y equals kx plus like.
What does it mean for the painters and the painting? That's what I'm asking. So yeah, you're getting at the right idea, but what does it mean for the painters and the painting? Tell me.
Painter 2 already had 250 painted, 250 square feet painted when the first painter started.
Okay, so he's saying that, so when painter 1 started, painter 2 had already done some amount of painting.
Well, isn't the 1.5 just the change in the painting? It's not like the starting point.
Okay.
So it's just like the change in the, like, so they start at a certain point, doesn't matter where they start, but 1.5 is the change, like how much faster the change of painter Y paints than the change of painter X.
Okay. It goes back to an earlier question. When painter 1 had painted 0, had painter 2 painted 0? Is that possible? If they painted at this constant rate of 1.5, and we know that at 100 it was 400, there's no way they could have both started at 0, because then it would have been a constant rate. It would have been 4 to 1 relative size, relative speed. Okay, so what I want you to do is, I want you to use, forget every formula and method you've learned in the past. Use the idea of rate of change to figure out how much the second painter had painted when the first painter started. Okay, so you're using reasoning, step-by-step reasoning to figure that out, rather than, oh, I think I remember how to solve for B. You know, so can you do it using reasoning, using things like x, values of x, values of y, delta x, delta y. Okay. So, reasoning about these types of quantities, can you figure out how much painter 2 had painted when painter 1 started? Work with your partner. Go.
Constant for painter is
That also makes the change in x0 at this point. It's still sorry. Oh,
Hey, is it Adra?
Yeah.
Did you have any success? Can you get us started?
Like where they started at.
So we want to use reasoning about rate of change to figure out how much painter 2 had painted when painter 1 began painting.
Well, when painter 1 had painted 250 square feet when they began painting, because then once the painter 1 started painting 100 square feet,
Okay.
then they painted another 150 square feet from starting from 250.
Okay, so it's great reasoning, but it's great reasoning knowing what the answer was. So yeah, so no, it's really good reasoning. She's saying the answer is 250. So here's what I'm going to do. I'm going to say it's 250 because if painter 1 painted 100, then how much did painter 2 paint?
1.5 times.
1. Which is how much?
150.
150. And then that so I have the 250. 150 would be the additional amount, which would get me up to 400. So can anyone reason it without knowing the answer first? Will.
You would say that that point would be 0 for painter 1 is at the same y, 150. So at the painter 1's starting point.
If we know that when it's 100, it's 400, what delta x are we interested in? So we know that when x is 100, y is 400. What delta x are we really talking about? 0 to 100? No, actually, we're here. So it would be, is it Nathan? What if I'm here, what delta x takes me to 0 square feet painted for painter 1? I'm here at 100. What delta x is going to get me to where I want?
I zoned out for the first half.
What's that?
I wasn't really paying attention to the first half of that. So.
You want to answer the question again?
Yes.
Okay. Here I am. Painter 1 at this point has painted 100 square feet. What delta x do we need to kind of execute so that delta 1 is now painting 0, has painted 0 square feet? What would delta x be? What is that change? Negative 100. And we know, given any change in painter 1, we know immediately how to find how much painter 2 painted. How much did painter 2 paint? This is not 100 times K, sorry. This is... If painter, given that painter 1 changes the amount he paints, how do we find the change in the amount? Adra, how'd you get that? It's the ratio between the two. So the change in painter's 2's amount of area is always 1.5 times. Remember? If you're still not sure, learn it now. Never forget. For constant rate of change, the changes are proportional. The amount painted, or the change of y, is always this constant amount times change in x. So what was the change in y? Change in x was negative 100. What was the corresponding change in y? Negative 150. So this is exactly what Adra said at first, but just starting from where we're going to end up and going back, which was great. Okay, so then the initial amount that painter 2 had painted was 150, right? No. What's the negative 150 represent? Change in y. So what's the new value of y? We started at 400. We changed by 150. We end at 250. So the new value of y is the old y plus the change in y. And how do we get the change in y? Using rate of change, right? Using proportionality of changes, knowing that delta x, delta y will be 1.5 times that. And then we'll just add that to the old value of y, and that'll give us the new value of y. Does it make sense? Okay. Anybody have a question? So let's generalize this now. I'm going to erase. Suppose I started at this point, 100, 400. And I want to know, so let's turn the axes on. Okay, so ignore the numbers on the axes. We know this is 100, 400, okay? So I want to know for any x value, what will the corresponding y value be? So let me turn that on and do it. So don't look at the numbers here. That x represents any amount, total amount painted by painter 1. And then there's the corresponding amount by painter 2. So here I am. We know that at 100 it's 400. We know the rate of change. And now we want to say, I want to know the total amount painted by painter 2 given any changeable amounts painted by painter 1. How can we do it? We've got all the tools. We've got everything we need. How do we want to start? Will?
Since we've seen through our x and y values on this table, since y started at 250, it's always seemingly 1.5 times the x value plus 250.
Okay, mx plus b, right? So let's forget that we knew the 250. So yeah, it's right. It's good reasoning. It's good. But forget about the 250. We want to focus on. We want use this 100, 400 point. So how can we use the 100, 400 point to get started if we want to know what the y value is for any x value starting at the 100, 400. How are we going to start? Same way we started before. Roman, any idea?
Would you find the change from where x is to where you initially started at 100?
Nice. So you want to find the change in what?
From x minus 100.
Okay, so he wants to find the change in x first. It's a good start. What is the change in x from our variable point, from 100 to our variable x value? Will?
Would be your x minus 1.
Yeah, that's what Roman said. Do you see it? So it's this distance right here. It's our change in x. And it's x minus 100. Off to a good start. What's next? Somebody else. Where are we going to go from here? What's our goal? Given x, we want our goal is, let's say the goal. We want to find that y value. So what are we going to do? Somebody knows. Nathan.
Well, do we know what day is right now? Or do you know?
Yeah, it's the same. It's the same situation.
Yeah.
It's the same. It's the same painters.
Well, so we just figured out. Hopefully, if we know what delta x is, we just plug in delta x.
Yeah. So if painter 1 changes the amount he's painted by x minus 100, then we can conclude. Somebody. Yeah, Saskia.
Changing y is y minus 400.
How do we get the change in y from the change in x?
Oh, from the change in x?
Yeah. Same way we've been doing it all along. It's always 1.5. Whatever the change in the painter 1 paints, painter 2, his additional amount painted is 1.5 times that. Always, right? Proportionality of the changes. So now, what is... We got it. We're home free. So what's the new value? Given any variable value of x, what will the value of y be? Somebody knew? Isabel. So what is this value of y?
It has to be delta y minus 400. No, it'd be 400 plus the delta.
400 plus delta y. That's it. You got it. Nice. So a lot of you were thinking, it's the starting point for y here, and now we're going to change by this much. And how much is this much? What was delta y? 1.5 times x minus 100. So y equals 400 plus 1.5 times x minus 100. Okay? What's the idea here? What's the idea of, given any amount the painter wants painted, I want to know the amount determined amount by painter 2. What's that idea? Just general idea. We've talked about it. Here it is. Knowing how much painter 1 has painted total determines how much painter 2 has painted. What is that? Yeah, but y and x are not proportional. Y and x are not proportional. So I'm looking for more of a general idea. Given that you know one quantity, what determines the value of the other quantity? It's function, right? This is function. So this thing we're developing is linear function. So we could call it like the painter's function, px. Px equals 400. Initial amount of y plus how much y changed. Okay? So in general, a linear function. So let this point be any point that we know. X, we call it x naught, y naught. And our rate of change is k. And we know that's m, right? So that's m, slope of the line. Given any point x naught, y naught, the rate of change, which is the slope, how can we find y given x? So you write it out. So this is for any function. You write it. Starting at any point x naught, y naught, with a rate of change, we'll call it m for slope. What can we write any linear function as? Richard, go for it.
L of x equals mx plus b.
No, that's not. That's just what you remember from the past.
Yeah.
Let's use what we just learned in the last 3 days.
So L of x would be y naught
Y naught, the original value of y.
plus slope, which is your n.
In general, what are we going to add to y naught to get?
You're changing that.
We're going to add the change in x? In general, what are we adding to y naught? Change in y. So it's the starting value of y, now plus how much y changed. And how much did y change? For any function then. M or k, doesn't matter, m or k, times x, delta x, right, which is x minus starting value of x. So, again, change in x, x minus the starting value of x. That's how much x would change. How much y would change, we know, is 1.5, or this, whatever the rate of change is, times that. We add that change to the original value of y, and it gives us a final value of y corresponding to the starting value of x. So this when we starting next week, this idea or this way of thinking about linear function is going to be what's going to help us. This is what we're going to build upon. Okay? Because what we're going to need to do is we're going to need to build a linear function that's actually many linear functions pieced together. This is going to be invaluable for doing that. Okay? So we're going to take, like I said, take many linear functions, piece them all together. This way of thinking about it is going to be the most convenient. So notice what happens. So let's go back to our painter's function. We wanted that amount that painter 2 had painted when painter 1 hadn't painted anything at all. So how would we use this to do that? Yeah, so what's the output of this function represent? Which is how much painter 2 has painted, right? The output is how much painter 2 has painted given the input of how much painter 1 has painted. All right, it'll reproduce any line on this any point on this curve, that function. Okay, that function, this function right here, produces every single point, all infinitely many points on that line. Is what this produces. Plug in how much painter 1 has painted, it spits out how much painter 2 has painted. Okay, so we wanted to know how much painter 2 had painted when painter 1 had painted nothing. So what do? Someone said it. Ben.
Plug in 100 for x, because you're going back, or plug in 0 for x.
Right.
X minus 100.
Yep. So.
Then it'll end up putting you like.
Yeah, remember the process we went through? If you plug 0 in here, then what does the parentheses represent? 0 minus 100 represents? Change in x. What does 1.5 times negative 100 represent? Change in y. And then y, we add it to 5, the original amount of y to the change in y gives us y, 250. Plug in 0, you get negative 100 times 1.5 is the change in y. Taken or added to the original y gives us the final value of y. This works then for any linear function. Okay, I will post homework this afternoon. not send you an email. It'll just be up sometime this afternoon. You can check tonight or tomorrow. And I'll try to get results for that exam maybe Sunday. Have a good weekend.
My weekend works.
Mr. Ashburn, I just realized something. When I took my exam, the lady, whoever gave me the exam, didn't actually give me a Scantron sheet.
Okay.
So
You never got a Scantron?
I didn't.